Welcome to the 10th part of mechanical properties of fluids. In this part, we will study about applications of Bernoulli's theorem. Dynamic lift. Dynamic lift is the force that acts on a body such as on an airplane wing, a hydrofoil, or a spinning ball, by virtue of its motion through a fluid. In many games such as cricket, tennis, baseball, you have noticed that a spinning ball deviates from its parabolic trajectory as it moves through air. This deviation can be partially explained on the basis of Bernoulli's principle. Ball moving without spin. Firstly, we will consider this one. When a ball is thrown horizontally with a large velocity and at the same time given a twisting motion to cause a spin, it deviates from its usual parabolic trajectory of spin-free motion. This deviation we will explain here. Figure shows the streamlines around a non-spinning ball moving relative to a fluid. From the symmetry of streamlines, it is clear that the velocity of air above and below the ball at corresponding points is same, resulting in zero pressure difference. The air therefore exerts no upward or downward force on the ball. Now consider the second situation, ball moving with a spin. A ball which is spinning drags air along with it. If the surface is rough, more air will be dragged. As shown, the streamlines of air for a ball which is moving and spinning at the same time. The ball is moving forward and relative to it, the air is moving backwards. Therefore, the velocity of air above the ball relative to its larger and below it is smaller. The streamline does get crowded above and rarefied below. This difference in velocity of air results in the pressure difference between the lower and the upper faces, and there is a net upward force on the ball. This dynamic lift due to spinning is also called as Magnus effect. Aerofoil or lift of an aircraft wing. Aerofoil is the name given to a solid object shaped to provide an upward vertical force as it moves horizontally through air. This upward force, or you can say the dynamic lift, makes aeroplane fly. As shown in the figure, the cross-section of the wing of an aeroplane looks like an aerofoil. The wing is so designed that its upper surface is more curved and hence longer than the lower surface, and the front edge is broader than the rear edge. As the aircraft moves, the air moves faster over the upper surface of the wing than on the bottom. According to Bernoulli's principle, the air pressure above the upper surface decreases below the atmospheric pressure, and that on the lower surface increases above the atmospheric pressure. The difference in this pressure provides an upward lift called dynamic lift to the aircraft. And because of this, there is an upward force resulting in a dynamic lift of the wing and this balances the weight of the plane. The following example illustrates this. It's your NCERT example 10.8. A fully loaded Boeing aircraft has a mass of 3.3 into 10 to the power 5 kilogram. Its total wing area is 500 meters square. It is a level flight with a speed of 960 kilometer per hour. You have to find the pressure difference between the lower and the upper surfaces of the wings and the fractional increase in the speed of air on the upper surface of the wing relative to the lower surface. And the density of air given to you is 1.2 kilogram per meter cube. For the first part, the weight of the Boeing aircraft is balanced by the upward force due to the pressure difference, as we have discussed in the last slide. So mg must be equals to P1 minus P2 into A. That means mg divided by A must be delta P. So by putting the values, you will find out that delta P comes out to be 6.5 into 10 to the power 3 Newton per meter square. For the second part, let us suppose V1 and V2 are the speeds of air on the lower and upper surfaces of the wings of aircraft, and P1 and P2 are the corresponding pressures. So by using the Bernoulli's principle, P1 plus half rho V1 square must be equals to P2 plus half rho V2 square, because horizontally they are on the same height, so that portion rho GH will not be. We have to consider. So P1 minus P2 is equals to rho by 2 into V2 square minus V1 square, and from this one you can find out the value of delta P. Taking the average speed V average equals to V2 plus V1 divided by 2, and the value will come out equals to 267 meter per second. So by putting in the equation, you will get V2 minus V1 divided by V average equals to P divided by rho V average square, and that will come out 0.08. That means the speed above the wing needs to be only 8% higher than that of below.